Welcome back, everyone, to the last session of our mini white dwarf workshop. And the last session, we're going to talk about transients related to white dwarfs. And the first talk is coming from two speakers. We have Brian Metzger speaking, as well as Elias Aydi. And take it away, Brian.
Thanks. So I'm going to talk a little bit about the theory a little bit, and then Elias will hopefully back up what I say with some observations. So I'm going to be talking about some shocking new insights into classical nova. Obviously, there's some of the most common transients in our galaxy, oldest ones. But we really have a revolution in our understanding of what powers the emission from these events across the electromagnetic spectrum in the last decade, and I want to give you some insight into that. You can find more information in this recent annual reviews article that Laura Chomiak led, and it's on the archive. Will be in press soon. I can't advance. Okay. So nova are when we have runaway burning of hydrogen on the surface of a white dwarf. We typically call it a classical nova when the transferring object is a main sequence star, or an embedded nova or symbiotic nova when it's a giant companion. This thermonuclear runaway leads to expansion of the hydrogen envelope, eventually to its ejection and the resulting mass loss and the production of quite a bit of light, which allows us to see these events across the galaxy. These are not destructive events. They recur once you've had a chance to build up another layer of accreted hydrogen, and the recurrence time, as shown in this diagram with the dashed lines, can vary from millions of years to as short as a year, depending on the mass of the white dwarf and its accretion rate. Understanding nova is critical to many aspects of CV evolution. Single degenerate 1A supernova, we need to know, is the white dwarf gaining or losing mass on net? Is the binary gaining or losing angular momentum? These are critical questions, and I hope I'll try to convince you that we don't understand this in great detail, despite decades of really amazing work. It's a field that really requires a lot more to understand fully. So the optical light curves of nova, some examples are shown here on the right. They typically rise to their peak within a few days and then decay over a much longer time scale of weeks to months to years. The decay time is generally attributed to the time it takes to remove the hydrogen envelope. And the mechanism by which the envelope is removed remains uncertain. There are a number of different possibilities. The peak luminosities are comparable or even in excess of the Eddington luminosity of the white dwarf, which is a bit of a mystery given that these have largely been modeled as hydrostatic events, effectively. The ejecta velocities can vary from hundreds to thousands of kilometers per second, and in fact will vary within a given nova. And the ejecta masses can go up to 10 to the minus 4 solar masses. And once the envelope is removed, you reveal the central white dwarf, which is a source of luminous soft X-rays, burning the residual hydrogen layer. And those X-rays can photoionize the ejecta, and that produces thermal radio emission. But by and large, at least until the last decade, these were understood as a thermal phenomenon: thermal optical emission, thermal radio, thermal X-rays. But as I'm going to argue, despite the seemingly simple picture, a beast, powerful shocks lurks within many of these events. And I think some of the first evidence of this came from the radio emission. So this is showing you flux density versus time. As I mentioned a second ago, on timescales of years, you see photoionized emission, thermal emission produced by the expanding photoionized ejecta. But at earlier times, you often see an additional component of non-thermal emission, much higher brightness temperature, which most certainly is a result of internal shocks within the ejecta, for instance, producing synchrotron radiation. You see the same evidence in X-rays. So in addition, so this is an X-ray luminosity and hardness from one particular nova. And in this particular case, around day 200, you see that the X-rays get very bright and very soft, and this is the onset of the super soft phase as the white dwarf is being revealed. But prior to that phase, you see a much harder emission, which is more consistent with hot shock gas, maybe thousands of kilometer shocks producing 10 to the 7 K gas. Now, albeit the X-ray luminosities before or after the super soft phase that come from this shock component are quite low compared to the bolometric output of the nova, that was sort of, as a result of that, I think these were kind of seen as sort of a side feature of the event, maybe not crucial to what's going on. But I think that the relevance of the shocks became apparent following the discovery in 2010 of GeV gamma rays, and coincident with a number of these number of these nova. So on the left, I'm showing you here the first 4 events. On the right, I'm showing you the gamma ray light curves from those events. Typically, the gamma rays are roughly contemporaneous with the optical. They have luminosities of 10 to the 35 to 36 ergs per second. And they are produced by the acceleration of non-thermal particles at shocks, which then interact with other ambient light or particles to generate the gamma rays. So this may not, again, seem like a large luminosity, but if you think about it, shocks only put a small fraction of their energy into these relativistic particles, and only a fraction of that energy is radiated in the gamma ray bandpass. So if you see gamma ray luminosities in this range, it implies shock powers which are actually considerable and comparable to the bolometric output of the event. And there have now been about 15 of these gamma ray detections, and by and large, it's a flux-limited sample, meaning we're mainly detecting the closest events. And so this is consistent with most nova having these shocks and generating gamma ray emission at some level. So the key question is, what is the nova ejecta colliding with? In the first gamma ray detection, it was one of these symbiotic nova with a red giant companion. So it was pretty obvious the ejecta was colliding with the dense wind of the red giant. And that worked pretty well for this first event. But since that time, essentially all of the detections have been of the classical variety, where the companion is a CV, a dwarf with a wimpy mass loss rate and an even wimpier mass transfer rate. So it's very clear that the environment probably doesn't supply the working surface we need for these shocks, which is strongly suggested that the shocks are internal, meaning they're between different components of mass ejected during the nova itself, as opposed to interaction with some external environment. So let me just go through what we think is the cartoon picture of the shock interaction, and hopefully Elias will supply some justification for this. So we have the TNR, which produces the expansion of the nova envelope. It comes to encase the Roche lobe of the binary. We think the early phases of this are characterized by mass outflows that occur, for instance, through the outer Lagrange point. But in any case, is strongly shaped by the presence of the binary and is concentrated in the equatorial plane with a relatively low velocity comparable to the orbital speed. But then after a few days, for some reason, the outflow transitions into more of a faster outflow coming from the white dwarf, and being faster, it's less influenced by the binary. Maybe this is a radiation-driven wind. And so it comes out more spherically. And then obviously now you have a fast outflow inside of a slow one, and there will be shocks and the collision between these two. Predominantly, we think in the equatorial plane, which generates the gamma rays, but then in the polar regions, the matter will be more or less free to expand. And evidence for this is supported by VLBI imaging, radio imaging of this particular gamma ray nova, which at early times, relatively early times, day 126, you see this sort of bipolar lobe-like structure shaped by the equatorial material. This is Laura Chomiak's very, very nice work. But then as you wait a little bit, this fast component dissipates, and now you see this slower equatorial component, which is substantially clumpier, coming out a little bit later. And we have other spectroscopic evidence supporting these two components of ejecta that I think Elias will describe. This is, again, work that's been done for many years by many people. You also see some evidence looking at old nova shells that are decades or centuries old. They show sort of ring-like structures, egg-shaped ejecta shells, strongly indicative that the binary is having an important role in shaping the ejecta. And we think the shocks are basically a symptom, if you will, of that interaction, which is shaping the geometry of these ejectas. So one thing I want to emphasize to you is that the shocks in these events are radiative. So the gas is sufficiently dense during the gamma ray emitting phase. It has to produce a lot of gamma ray luminosity, that the post-shock gas effectively immediately cools through radiation and becomes very dense, much faster than the expansion time scale of the materials. These are radiative shocks. And this has the implication that most of the shock's luminosity must emerge as radiation in some waveband. We just have to figure out where. So let's zoom in a little bit on the dynamics of these shocks. So we have a fast outflow colliding with a slower outflow. This drives a forward shock into the slow outflow and a reverse shock back into the fast outflow. The gas behind the shocks, as I mentioned earlier, immediately cools, and this produces UV and X-rays. But those UV and X-rays don't get very far. They effectively run into this neutral material. They're absorbed, and the energy from the shock is reprocessed to lower frequencies where it can emerge as optical radiation. And then the cool gas, of course, collects in a central shell between the two shocks. Now, the same shocks are also accelerating non-thermal particles through the Fermi mechanism, and as they're accelerated, they're then advected to this central shell, which is dense and is a nice location to make the gamma rays. So both for purposes of thermal particles, hot electrons, and for purposes of non-thermal particles, the shocks are, radiative. So what that means is that basically the shock power is both immediately manifesting as optical reprocessing radiation as well as gamma rays. And likewise, we should expect the component of the optical emission that is arising from internal shocks to track that associated with the gamma ray burst. This was a pretty clear prediction. And as Elias, I think, will also discuss, this has been recently confirmed. We had a nova where we had enough signal to noise on the gamma rays. We were able to see a correlation between the gamma rays and the optical emission. And this has a number of important implications about these events. For instance, it does suggest that a significant fraction of the optical luminosity, particularly the variable parts of the light curves, we didn't really understand that well, may be powered by internal shocks. They're not directly originating from the burning layer of the white dwarf. It also suggests that you could achieve super Eddington luminosities without violating the Eddington limit, because you're dissipating a kinetic energy of an outflow. It's not a hydrostatic luminosity from the white dwarf. And also, I'm not going to talk about it in this talk, but if you measure the ratio of the optical essentially tells you the total shock power, and the gamma rays tell you the non-thermal power, and the ratio is telling you something important about the particle acceleration efficiency at these shocks. And I always want to make the connection between interaction, powered supernova. Oh, out of time? Yeah. Okay. Give me one second. I'll just finish. So again, we have many of the brightest supernova we think are powered through the same mechanism, where the supernova ejecta is colliding with some dense circumstellar material, and that reprocessing of the energy through shocks is what's causing these supernova to be very bright. Canonical example being 87A when it collided with the shell around it. So the final thing I'll very quickly say is that we have a mystery, which is if the optical is indeed reprocessed shock luminosity, we should be able to see the X-rays from the shock. If we go to New Star, which is above, where it's not being absorbed, we should be able to measure the X-rays and then infer what the unabsorbed luminosity of the X-rays are. And we're still finding that the X-rays are quite a bit wimpier from these shocks than we would have naively guessed. And so there is this open question as to why they're so dim. And again, I'm running out of time, but these shocks are fascinating, these radiative shocks. They're prone to all types of instabilities. The gas behind them is a multi-phase medium, which can suppress what you naively think from the 1D jump conditions about what the emitting temperature of the gas should be. And so it's really fascinating, and I think this may be able to suppress the X-rays, but there's a lot of work that needs to be done. So I'm just going to finish by just saying that it's clear that these shocks play an important role in the nova, and I want to clear with some implications. It's clear that there are multiple modes of mass loss in the nova. There's a common envelope-like outflow. There are winds. There are abrupt transitions between them that are causing these shocks. And it really, I think the open question in this field is how do we, can we capture this in 1D models? How do we model all this multi-dimensional effects while also capturing the nuclear physics near the surface? And again, what are the implications of all of this for binary evolution? So I will finish there. Thank you.
Thank you, Brian. We'll go to Elias' talk and then do the questions after Elias's talk. Oh, we just saw your slides. And
yeah, I couldn't unmute myself on the slides. So, okay, can you see my slide now?
Yes, we can.
Hi, my name is Elias. I'm a postdoc at MSU working with Laura Chomyork. And of course, what I'm going to show today is a collaborative work and not a solo work, of course. So as Brian mentioned, okay, my slides are not moving. Are they moving now? Okay. So as Brian mentioned, the standard paradigm of Novae predicts that the luminosity of a nova is powered by a thermal emission from a hot white dwarf. But this picture has been challenged recently, especially by Fermi LAT detecting GeV gamma ray emission from several novae. And it was a shock. No, literally a shock, because as Brian mentioned, we need shocks to accelerate particles to relativistic speeds so they emit gamma rays. One of the current models suggested now to explain the formation of these shocks in Novae predicts that the shocks occur at the interface of two aeroflows. Initial slow dense ejection, possibly directed in the equatorial direction by the binary motion, followed by a faster wind, which slams into the slower ejection, producing gamma ray emitting shocks. This scenario is mainly based on the radio imaging of a 2012 nova called V9591. The color images here I'm showing are thermal emission, while the black contours are synchrotron emission. And early on, we see some blob that is not very well resolved. Then we start seeing two distinct blobs moving in one direction. And 2 years later, the symmetry flips, and now we can see two blobs moving in a perpendicular direction. So what we think is happening is that initially we cannot resolve the nova ejecta, but later we start first resolving the faster bipolar flow, which is expanding at greater speeds. 2 years later, the fast flow has dissipated, and now we can resolve the initial slower and dense flow. The model predicts that the X-ray emission from the heated gas by the shock is absorbed by the dense ejecta ahead of the shocks, reprocessed into lower energy. So we see mainly optical and gamma rays from the shocks. The observed gamma ray luminosity from novae that have been detected by Fermi LAT so far range between 10 to the power 35 and 10 to the power 36 Kelvin, which is around 1% of the electric luminosity of a nova. So although this number seems small, but as Brian mentioned, based on the standard gamma ray emission mechanism, we expect that like fraction of a percent or like 1% of the shock luminosity to be emitted in Fermi gamma rays. So if we compare these two figures, we can assume that shocks could potentially power a substantial fraction of the electric luminosity of a nova. So of course, shocks have been theorized to contribute to the luminosity of other events such as appearance supernovae, stellar merger, star disruption events, but direct observational evidence has been so far lacking. The first observational support for this model came in 2016 with a nova called Assassin 16MA, which optical light curve in blue here and gamma ray light curve in black were correlated. I know correlation doesn't necessarily mean causation, but there's no reason for the optical and gamma ray light curves of a nova to follow each other unless they share the same origin, which is presumably the shocks. Well, if Nova Assassin 16MA did not convince you, Nova Assassin 18FV or V906 Carino will convince you for sure. This nova was discovered by Assassin in March 2018, and it was a bright naked eye nova. And we were very lucky with this nova because one of the satellites of the bright nanosatellite constellation was observing the same field of the nova when it erupted. This led to one of the best sampled optical light curve for a nova to date, tracking the eruption from its start and showing multiple short-lasting flares of the order of a couple of days and with an amplitude just shy of the magnitude. Okay, we have this very beautiful light curve, but what did Fermi see? Unfortunately, when the nova erupted, Fermi was not observing due to technical issues with solar panels. But when Fermi came back online 23 days after the eruption, this is what we got. Again, the best sampled gamma ray light curve of a nova to date, showing multiple distinct flares correlated in time with their optical counterparts. And this is huge. The fact that these flares occur simultaneously in time in both bands means that they very likely share the same origin, which is presumably the shocks. And the fact that the luminosity of the nova doubles during these flares means that shocks will indeed power a substantial fraction of the electric luminosity of the nova. We also had new star X-ray observations at the same time as the optical and gamma ray flaring, and we detected faint X-ray emission originating from deeply embedded shocks. But as Brian mentioned, there is something that bothered us with the observation is that the X-ray luminosity is a bit lower than the models predict, and this could be due to suppression by the gas around the shocks. So this set of unprecedented space observation present us with the first, or like this direct observational evidence that shocks could indeed power the luminosity of stellar eruption. This is a screenshot from the NASA press release, and here I'm showing a video from the press release of what we think has happened during the eruption. So the video shows a two colliding flow scenario, but how did we conclude this? Did we have any imaging of the nova? Not really. But what we had, almost daily cadence, high resolution spectroscopy. I'm showing here the evolution of H alpha. And initially, during the rise to peak, we see preceding profiles with velocities of a few hundred kilometers per second. As the nova reach peak, we suddenly see broad emission emerging with velocities of more than 1,500 kilometers per second, while the preceding profile is still superimposed on top of it. This indicates the presence of two physically distinct ejections, with the fast one blowing from the inside of the slow one. This also shows that high-resolution spectroscopy is an important tool to explore the ejection scenarios in novae. But of course, this is nothing new, and the presence of multiple spectral components has been reported since the days of D. McLaughlin, Celia Payne-Kapuskin, and alike. And they have associated these components with multiple shells of gas or ejections. However, there's still some debate in the field whether novae exhibit single ballistic ejection or multiple ejections. And it was not clear if what we observe in the radio images of nova V9591 is universal to all novae. So we use agile telescopes such as SOL, SOAR, and rapid nova discovery reports from surveys like ASSASSIN, as well as the contribution from citizen scientists to try and observe as much novae as possible before they reach optical peak. And we found an interesting trend in all these novae. Here I'm showing a sample where we first see a slow peak signal profile before peak on top, and then after peak, a broad emission emerged with the peak signal profile still superimposed on top of it. So this is very similar to what I just described for Nova V906 car, where initially we have a slow dense flow manifesting as a pre-maximum peak signal profiles, and then we have faster wind manifesting as broad emission. And when these two large flows interact, they create shocks which emit gamma rays. The fact that this same spectral evolution is observed in all novae in our sample indicates that this two-flow scenario is probably universal. Now, some of you might think or ask why the fast component always appear around the optical peak. Well, maybe because the interaction between the fast flow and the slow flow is what is driving the optical peak. And now we have a great deal of evidence that shocks could indeed power a large fraction of the optical emission of novae. Actually, I did not tell you the full story because also at peak, a third component appears with an intermediate velocity between the slow and fast ones. Here I'm zooming on the lower velocity and we see this distinct component, which is faster than the slow one, appearing also at optical peak. The pioneering studies of nova spectroscopy did not settle on why this component always appeared at peak. But this could very well be the spectral signature of the gamma ray emitting shocks, which are powering also the optical peak. That is why these components always coincide with the peak in every nova. Some recent work by Munari et al. Showed that nova optical light curve could actually be the combination of two light curves, more precisely, emission from the fireball as the ejecta initially expand, and then the shock emission, which manifests as the main optical peak. This is, of course, reminiscent of the double peak light curve that we observe in stellar mergers.
1 minute left.
Wrapping up, I'm almost done. Given that we are uncertain about the X-ray signature of the shocks, we decided to survey the X-ray behavior of novae during the early days of the eruption. So my previous student, Alexa Gordon, analyzed the SWIFT data of all gamma ray emitting novae for her underground thesis, and her results showed that there is no X-ray dissection by SWIFT during the gamma ray emission phase. And only after the gamma ray emission drops below detection limit, we start seeing hard X-ray, likely coming from the shocks as the ejecta become more transparent. The only nova in our sample with a concurrent X-ray gamma ray detection is nova V407 Cygnus, which, unlike the other novae, has a giant evolved secondary. This exception supports the scenario where novae with giant companion produce shocks with external circumbinary material, in comparison with novae with dwarf companions where shocks occur internal to the dense nova ejecta. Thank you very much. And I can leave you with my summary.
So thank you to Elias and Brian. Let me ask everyone if we have questions. I see one question already from Dan. Do you want to unmute and ask your question?
Yes, thanks, Sylvia. So this is really cool stuff. I mean, I'm referring to both talks. So if I understand correctly, then really a large, maybe even dominant fraction of the total energy released that we see is not thermal from the radioactivity from the explosion, but rather from these shocks. So how does this affect the assessment on how much mass was accreted, and maybe this is also relevant to the old question of whether novae grow or not, specifically towards the Chandrasekhar mass and so on.
Brian, do you want to take that?
Yeah, so we should be clear. We're not changing the. You're definitely right in terms of we're not changing the general way nova work, that they're ultimately powered by thermonuclear energy. It's just we're basically saying that some of that comes out directly as light, some goes into kinetic energy of an outflow, and then these shocks are tapping into that kinetic energy and powering some of the light indirectly. In terms of our ability, I think this does suggest that, you know, we have to be really careful when we're, you know, modeling the event using the models directly to infer the mass outflows. You know, there are ways to measure the ejecta masses, you know, using radio and optical techniques. I don't think this necessarily affects those, although if someone was assuming, you know, too simplified of an ejecta structure that wasn't accounting for the shocks or the multi-phase medium that these shocks might generate, they could end up with, you know, inaccurate masses, I suppose. But I don't think we're, you know, fundamentally changing that aspect of it. I think you know, there still is the question of, is the white dwarf growing in mass or losing mass? And I think the other really key question is, what is the angular momentum of the binary? You know, people can measure the orbital periods before and after nova, and that has sort of given mixed results on these things, and they're all kind of coupled together. This is sort of a wishy-washy answer. Maybe Elias wants to add something.
I think what you mentioned pretty much summarizes it. Yeah.
I mean, so yeah, I think it's still an open question. I think the big message here is that these are complicated things and we can't assume that we, you know, understand them yet.
Thanks.
Then we will go to Solen.
Hello, I had just a quick question, one question, perhaps one comment. And the comment comes first in the sense it also perhaps could be a question. That the radiativeness of the shocks is a little, it seems a bit shaky in the sense that the X-rays are not luminous, which would mean that the shock in terms of its evolution is perhaps at a more of a snowplow stage and momentum conserving stage. It's not a radiative remnant itself from just looking at the X-ray evolution. And therefore, I don't know how that would reconcile into the particle acceleration, but you do need to draw some of the thermal energy into the particle acceleration. Therefore, you cannot be radiating everything. So perhaps once a remnant is in a complete radiative stage, even the X-rays, that would be difficult. It will be more difficult to accelerate particles. Therefore, seeing the X-rays not very radiative is actually a good thing. So not very luminous, which would mean that it still, the remnant is drawing energy. Therefore, it's putting it into the particle acceleration, perhaps. That's one thing, perhaps a comment I would make for a general thing, and that the radiativeness and perhaps it could be just a nomenclature type thing. But one question I had about the very nice the gamma ray peaks and the optical peaks sort of being detected simultaneously. Was there some delay in this? Do I recall that correctly, or maybe I'm confusing with another source? Or was there some delay between the gamma ray and the optical peaks?
Thank you for the question. Yeah, I have this slide just after my summary slide because I was waiting for this question. Although like we had two of the best sampled gamma ray and optical light curves we have for NOVA, still we couldn't measure a proper delay with uncertainty over 2 sigma. But we measured the delay of around 5 hours, 2 sigma uncertainty, where the gamma ray is leading the optical. So this somehow support the suggestions that actually the optical is reprocessed X-rays from these.
X-rays or no. So this is some sort of illumination from the gamma ray emission of the optical.
Well, there could be delays either way. If there's some time scale that it takes to accelerate the particles, you could imagine the gamma rays might lag the optical, which is itself X-rays produced promptly, or you could imagine the other way around. If the optical was embedded and had to diffuse out of the ejecta, there could be a diffusion time delay. But I think, you know, we don't expect these delays to be large. So I think that is consistent with what's seen. But which direction it goes is a little unclear.
Mhm.
I think the other thing is we can talk more about this online, but I think there is a difference between radiative evolution of a supernova remnant and the shocks in this event, because with a supernova remnant it turns radiative at late times, and these, because they're internal shocks, when you're in earlier times things are denser because you're closer in, and so the shocks are actually more radiative, and then they become adiabatic. So I'm not sure that I would agree that being radiative suppresses the particle acceleration. It's, on the microscopic scale of the shock, there's still a shock front, and then behind the shock it cools over a longer length scale. But in the immediate vicinity of the shock, they should be able to accelerate particles, even if it's radiative. So maybe we can talk offline about this.
Yeah, you just one last, just the last sentence.
I think we have to.
Okay. I mean, it was not an argument. I was just going to make a comment. That's all. Okay. Thank you.
I want you to put it on Slack so we can continue this there.
Okay, I can try that. Okay, sure. Bye.
Sorry for that. And I'll ask Saurabh to start putting his slides up. I think there was also a question from Alexei, if you want to put it on Slack.